So constraint optimization is sort of the obvious generalization of the constraint satisfaction problem. Basically, instead of our constraint functions being Boolean, they are now real value functions. So we have some constraint functions, f of, let's say, f1 of x1, xn, and the function returns a real number. And our goal is then to, there's going to be, f2 and so forth. There's a bunch of these. And the goal now is, instead of finding an assignment to variables that has no constraint violations, is to find one that, minimizes the sum of the constraints, right? So the sum of fi, x1 through xn. So we want to find the argmin, or the values for the x's that minimizes the sum of all those constraints, or costs. We can usually call them costs or constraints, or sometimes we say these are utility functions, and then we want to maximize the sum utility functions. So that's it, right? So this comes in handy in when you have, if say in the graph coloring problem, you might have overconstrained problems. Like here is a little graph with 4 nodes. Say you only have 3 colors, right? So you have blue, green, and red. You cannot, find a coloring that doesn't violate any constraints. However, you can find, one that minimizes the number of constraint violations, which would be, say, this one, right? There's several, right? But basically, this one only violates 1 constraint. Versus, say, if you had them all blue, then you're violating all the constraints. That seems worse. So you can take, an overconstrained, this is overconstrained, constraint satisfaction problem. That means a constraint satisfaction problem that has no solutions, and turn it into a constraint optimization problem by just saying, each one of these has a weight of 1, and using that, and which is what we're going to be doing sometimes. So that's that. The main things about constraint optimization is, of course, since it's a simple, minimization problem, maximization problem. It has one and only one solution. Well, at least in terms of cost, right? So like here, there's only one solution, has a cost of 1. Although the actual colorings, there's a bunch, right? So this could be, you could see there's a lot of permutations that have that value, but there's only one minimal value. So that's nice, as opposed to constraint satisfaction, where you can have multiple solutions, or there could be no solution. So optimization has one solution in terms of cost. So cost. So that's it. And in terms of finding the solution, we're going to look at some algorithms for finding the constraint optimization problem. But generally, as you can imagine, is this very hard, exponential, to the end problem. So they are not feasible in practice. And what, as always, we end up doing is using some other approximation algorithms. Which are generally can be shown to be fairly quite good algorithms.